In this video, I'm going to show you how to use Euler's method to approximate particular solutions of a differential equation. Here we've got the initial value problem, dy dx equals a half y, with the initial condition that y of 0 equals 1. And we want to use Euler's method with a step size of 1 to approximate the value of y of 4 to 1 decimal place. Now, you might notice that this differential equation can be solved using separation of variables. You solve it using separation of variables and you just find that y equals e to the half x, and that graph is plotted here. We'll be using this graph for comparison with our approximations. Also, although this particular problem can be solved using separation of variables, most differential equations can't. So this approximation method that we're going to be trying out on this example will prove really useful in the future when we deal with non-separable differential equations. How Euler's method works for a step size of 1 is that we start with a known point, x0, y0. That just comes from our initial condition. The point here is 0, 1. And using that point as a starting point, we construct a sequence of approximation points with these two update equations. In these update equations, x is just increasing according to the step size. X increases by 1 each step, and then y increases by dy dx each step. Remember that the derivative at a particular point is just the rate of change of y with respect to x at that point. Remember that the derivative just tells us the increase in y per unit increase in x at a particular point. So if we step right 1 unit in x, then the y-coordinate we have to step up by dy dx units, and that'll give us a rough approximation. Alright, so let's try it out. So we're starting in this table here, n equals 0, we need x0, y0, and we get that from our initial condition. Initial x0 is just 0, that's from our initial condition, we're plugging in x is 0, and then our output there is y is 1. So for n equals 0, y0 equals 1. And then we just compute the derivative at this point, 0, 1. The derivative is just a half y, so that's just 0.5. We'll work in decimal here just because we'll be dealing with some kind of messy decimals. And we'll go ahead and apply our update equations here. So x increases by 1, so xn goes from 0 to 1. And then yn, that increases by dy dx. And dy dx is just 0.5, so we just add that 0.5 to the previous y value, and now our new value is 1.5. So our approximation here is that y of 1 is approximately equal to 1.5, and let's plot that on our graph. So 1.5 looks like it's about right over here, just a tad bit under the true point. So let's draw that. So something like that. So far it looks like a pretty good approximation. So now we're going to use this point 1.5 as the basis for our next approximation, and we go ahead and compute the derivative and then the update equations. First of all, the derivative is just half of y, so half of 1.5, that's 0.75. And then update equations tell us that we need to increase x by 1, so x becomes 2. And then y increases by dy dx, so 1.5 plus 0.75, well that's just 2.25. So that's our approximation for y of 2. Y of 2 is roughly 2.25, and let's plot that on our graph. So 2.25 is right about here. Alright. And now let's continue forward. So our new point is 2.25, and the derivative there is just a half y, and that's just 1.125. Update equations tell us to increase x by 1, so x goes to 3, and then increase y by the derivative, so 2.25 plus 1.25, and that comes out to 3.375. And so that's our approximation for y of 3. Y of 3 is roughly 3.375. And then, so let's plot that. 3.375. That's roughly like 3.4, which is right about over here. Okay, so we can see that our approximation is starting to be a little bit more off as we step away from our very first starting point. And that makes sense because each point is a little bit off. So the derivative we end up computing at each point will be a little bit off. But that's okay, this is just an approximation, and it's following the same kind of general shape of our function. That looks good. So let's just take the last round here. So let's plug in these points into the derivative and update. The derivative here is half of the y, so half of 3.375. That's just 1.6875. Since we want to round the value of y4 to one decimal place, we should keep like 3 to 4 decimal places in our computations here, just to avoid round off error. We can round at the end, but for now let's keep 3 to 4 decimal places. We'll do 4 just to be safe. So 1.6875 is our derivative, and then update equations tell us to add 1 to x and then to add dy dx to the existing value of y. So we get 5.0625. So there's y4. y4 is roughly 5.0625, and we can go ahead and plot that. That's roughly like 5.1. So y4 goes up to 5.1, and we're right about here. Okay. So okay, now we're ready to answer the final question. Approximate the value of y4 to one decimal place. So our approximation was y is roughly 5.0625. So our takeaway here is that y of 4 is roughly equal to 5.1 if we're just rounding to one decimal place. There we go. That is our solution. Now, a quicker way to do this process in the future is to include the step of computing the derivative. We just include that in our update equations. We can just substitute the derivative expression here into our update equations. And then the update equations would just be, well, x would stay the same, xn plus 1 equals the previous xn plus 1, but then the y update equation would become yn plus 1 equals yn plus, well, dy dx is just a half of y, so a half yn. And then we could simplify that and we'd get xn plus 1 equals xn plus 1, and then yn plus 1, well, 1 plus a half is just 1.5, which is like 1.5, so equals 1.5 yn. And then we could just use that to compute our y coordinates. Instead of having to compute the derivative each time, we can just build it in there. And you can see that this would work because initially our y coordinate is 1, and then using this rule times 1.5, we get to 1.5. Then 1.5 times 1.5 is 2.25. Multiply that by 1.5, you get 3.375. So yeah, you can go through this process a little bit faster by substituting in the derivative into the update equations right off the bat. One last thing to point out about this example is that we used a step size of 1, and in general that's pretty big when dealing with approximating differential equations. Usually step sizes are much smaller. Usually we actually put a step size into a computer and have it be really small and just have the computer do all the computations. And the advantage of using a small step size is that you get much more accurate approximations. With the big step sizes, you're using the derivative at a single point and just kind of assuming that the derivative doesn't change throughout your whole step. But it really does. The derivative is changing throughout each step, and if you decrease the size of the steps, you get to pick up on that change in the derivative, and the result is a more accurate approximation. So in this next example, we've decreased the step size, a step size of 0.25, so still something that is large enough for us to actually be able to do this by hand, but small enough to get a better approximation than before. But now we've also got an initial value problem that is non-separable. We cannot solve this differential equation by separation of variables. So this really highlights a good use case of Euler's method. We don't know how to solve this differential equation otherwise. Euler's method gives us a way to approximate some solutions to this differential equation. First of all, let's talk about how to adjust Euler's method for a step size of h, any step size h. Before we were using a step size of 1, now we want to use a step size of 0.25, but in general we could ask, like, how do we do Euler's method for any step size of h? So the idea is now we're increasing x by h each time. Before we were increasing by 1 each time, now we're increasing by h because h is our step size. That's how much we're moving in the x direction each time. And then as a result, our y approximation changes a little bit. Remember, dy dx is just the rate of change of y per unit increase in x, but we're no longer doing unit increase, we're doing an increase with the step size of h, so we have to multiply that amount by h. And when we choose small step sizes, this amount will get even smaller. So, okay, so these are the equations. You just got to put in h instead of 1 for the increase in x and the multiplier on dy dx, and we're ready to go ahead and compute this. So now instead of doing our table with x and y and dy dx, let's go ahead and compute the equations off the bat with the derivative substituted in, just so we have less work to do. So to start out our equations, we'll just write them down here. We've got xn plus 1 equals xn plus h, and h in this case is our 0.25, so xn plus 0.25, and then yn plus 1 is just equal to yn plus h, so 0.25 times the derivative, and the derivative is just given here, so 0.25 times xn minus yn, and we can simplify this a bit. So this is just xn plus 1 equals xn plus 0.25, and yn plus 1 equals, so we've got, well, we'll just write it out, yn plus 0.25 xn, and then minus 0.25 yn. So our final round of simplifying, we've got xn plus 1 equals xn plus 0.25, and yn plus 1 equals, yn minus 0.25 yn and plus 0.25 xn. So this is just 0.25 xn plus 0.75 yn. Alright, so these are our equations that we're going to be using, and we're starting with the point indicated by our initial condition here. X is 2, y is 4. So starting out with x is 2 and y is 4, and now we just have to iterate a few times. So let's go ahead and adjust our x. Let's update our x using these equations. So x is increasing by 0.25 because that's our step size. So we've got 2.25. And then how is y changing? Well, y just becomes 0.25 times the previous x, which was 2, and then plus 0.75 times the previous y. And we do that, we can just punch that into a calculator to save some time, and then we get the result is 3.5. Alright, and we can just keep on going. So now we just increase x again. So x increases by 0.25. Now we're at 2.5. And we want to keep going until we reach x equals 3, because that's the thing that we want to approximate. So x is 2.5 right now, and we can use our previous point to compute y. So 0.25 times 2.25 plus 0.75 times 3.5, and let's punch that into our calculator, and we get out the result of 3.1875. Again, since we want to approximate the final result to 1 decimal place, we're going to carry several more decimal places through our computations, just so we avoid any round-off error problems. 4 decimal places should be good here. And okay, so we just keep on going. So 2.5 plus our step of 0.25, and we get 2.75, and then update the y, so 0.25 times 2.5 plus 0.75 times 3.1875. Let's do that on our calculator, and we find our results. We'll just round this to 4 decimal places. It's going to be more than 4, but we'll just round it to 4. So 3.0156, and we'll take this through one more step. So increase that 2.75 by 0.25, then we've got x is 3, and that's the approximation that we want. We want our approximation when x is 3, and we can get that by just applying one more update to the y. So 0.25 times the previous x, 2.75, and then plus 0.75 times the previous y, which was 3.0156. Punch that into our calculator and get out the result rounded to 4 decimal places of 2.9492. Okay, so now we're in a good place to approximate the value of y of 3 to 1 decimal place. In our table here, we see our approximation is right here. So our approximation then, y of 3 is roughly rounded to 1 decimal place. That's just 2.9. And we're done. Again, remember that we can make our approximation even more accurate if we decrease the step size even more, and that's usually how it's done on computers to approximate differential equations. Step sizes are decreased to be very small because the computer can do many of these iterations much faster than humans can.